Right, so welcome to the second video in chapter 4. We'll finish up section 4.1 in this video. So we're talking about the sampling distribution of test statistics. And in particular, we might wish to know what is the mean and the standard error of that sampling distribution. So here's an example, a very small canned example. I have my entire population is these four values. W sub 1 is 3, W sub 2 is 4, W sub 3 is 6, W sub 4 is 6. By the way, pause, copy, play. Okay, so with such a small population, I can easily calculate the population mean and get 4.75. And I can calculate the population standard deviation. And since it's population, not a sample standard deviation, but the population standard deviation, I'll be dividing by 4 instead of 3, okay? So I take 1/4, I take 3 minus my mean squared, 4 minus my mean squared, etc., through all values of the population, and I get a population standard deviation of 1.299, okay? All right, now here's how I'm going to sample from my population. I'm going to draw two members at random from the population, okay? And I'm going to draw them with replacement, so it's possible I could draw the same number twice, like I could draw 3 twice, because I draw it, look at it, record it, put it back, draw another number, which could be 3 again, record it, okay? So I'm going to draw it with replacement and order matters, so I'm going to draw all possible samples of size 2, and since it's with replacement and order matters, there's 4 choices for the first number, there's 4 choices for the second number, so we get 16 samples altogether. And then the test statistic I'm going to record is the sample mean, okay? So in these 2 lines, I've drawn all possible 2-member draws, okay? So there's drawing W1 twice, W1 followed by W2, W1 followed by W3. There's W2 followed by W1. So we'll look, the order matters. Those are the same 2 numbers, but in different orders. So they're different slots. So I've drawn all possible 16 2-member draws from the population. And below them, I've just calculated the average of each one. So for example, W2 and W3, that would be 4 plus 6 divided by 2. That's 5 for the sample mean there, okay? So I get all possible 2 sample draws and their sample mean. So from these 16 values, I can calculate the mean of the test statistic. So the mean of these sample means. So I could add up all those sample means, divide by 16, and I get 4.75, which was exactly the mean of the population. And if I do the standard error of the test statistic, I'm going to do the square root 1 over 16. Again, it's 16 because I've calculated all possible 2 sample draws. So this isn't a sampling of all the possible 2 sample draws. This is all of them. This is the entire population of them. So I'm going to divide by 16 instead of 15. All right, so for each of them, I'm going to say, well, look, I've got a sample mean of 3 minus my mean of my test statistic of 4.75 squared, sample mean of 3.5 minus my mean of the test statistic, 4.75 squared, through all 16 of those sample means, and I get 0.9186. So if you note, the standard error of the test statistic, 0.9186, is not the same as the standard deviation of the population, though the means were, okay? All right, so there's an example, a small canned case where we can calculate both the mean and standard error of the sampling distribution of a test statistic. And the test statistic was the sample mean. All right, now we could have also done this theoretically, so without having to do any actual sampling. So my test statistic was x1 plus x2 divided by 2, the mean of 2 random draws, okay? Where x1 and x2 came from that population described over there, which had a mean of 4.75, had a variance or standard deviation of 1.299. So again, pause, copy, play. So if I want to calculate the expected value of the test statistic, I'm looking for the expected value of x1 plus x2 divided by 2, okay? From 313, we know we can drag 1/2 out. And since x1 and x2 are a random sample from the population, they're independent of each other. And by independence, I can split the expected values nicely. I can do that anyway. I guess I didn't really need independence for that. Expected value of x1, well, that's the mean of the population. Expected value of x2, that's the mean of the population. So I get 4.75. Could have also calculated the variance of our test statistic and then gotten the standard error of it. So the variance of t, well, it's the variance of that x1 plus x2 divided by 2. Now remember, when you drag a constant out of a variance, you have to square it. So there's the 1/2 squared. And now, since x1 and x2 are independent of each other, I can split the variance. If they weren't independent, there'd be that covariance term that you might remember from 313, which we'll encounter later in this course as well. So I split the variances. Each variance is the standard deviation squared. So if I sum that up, I get 0.9186 quantity squared. So I have my standard deviation is 0.9186 as on the previous board. So I could do it via sampling, exhaustive sampling, which was the first panel, or more theoretically, which was the second panel. All right, 2 more examples that I'll do one via R and via theory, and the other just via R. Okay, so why don't you pause and copy down this panel, and there will be some R here. All right, so here's what we're going to do. What we're going to do is we're going to sample 100 times from an exponential distribution with lambda equals 1/15. You'll recall that if lambda is 1/15, the mean of the exponential is 15, and the variance of the exponential distribution is 15 squared. Okay. All right, so we're going to sample 100. Once I sample, I'm going to record my test statistic, which will be x bar, my sample mean. And I'm going to repeat this sampling process 1,000 times. Okay. All right, so let's do it theoretically first, and then we can show how R can approximate some of this stuff. So theoretically, if I'm looking for the mean and standard error of the sampling distribution of our test statistic, I want the expected value of x bar and the variance of x bar followed by the square root. Okay. So just like in the last panel, the expected value of x bar is the sum of the 100 random samples divided by 100, drag out the 100, split the expected values. Each expected value is 15, so I have 1/100 and then 100 copies of 15, so I get an expected value of x bar of 15. For variance, just like on the last example, x bar gets replaced by the sum of the 100 samples divided by 100. Drag out the 100 as 100 squared. X1 up through X100 are random samples, so they're each independent of the others. So by the independence, I can split the variances. Each variance is 15 squared. So I have 1/100 squared times the 100 copies of 15 squared. So it looks like one of the hundreds cancels, and I'm left with 15 squared over 100. Standard error then is then the square root of that, which turns out to be 1.5. And those are precise and exact. Okay. So note the expected value of the test statistic matches that of the population, but the standard error of the test statistic does not match the standard error of the population. It's smaller, and we'll see why. Okay. All right. Now let's flip it over to R and see how R can automate some of this process at the cost of only giving us an approximate value. So you note these values do not correspond to the 15 and the 1.5, though they're close. All right, so again, in the folder for R, all right, so on line 20, starting on line 25, we're going to do a sampling distribution from an exponential with lambda equals 1/15. So I'm going to run this process 1,000 times. And you'll remember when I did the theoretical expected and standard error, I never used the capital N equals 1,000 samplings. I used the 100 because that was part of the definition of X bar. All right, so I'm going to create a vector on line 26. X bar has 1,000 slots in it to store my test statistic. And then lines 28 to 32 is my loop. Okay, so there's my loop. And this R exponential means random sample from an exponential distribution. And I'm going to grab 100 members of this exponential distribution, and there's the rate of my exponential distribution, the lambda. Okay. And then once I grab those 100 members of the exponential distribution, I'm going to calculate their mean, and I'm going to throw that into my vector x bar in the ith position. Okay, so let me run that code. Okay, and then I can create a histogram for it. There it is. I can see how normal it looks. And throw my line in there, and it's looking pretty normal, except on the edges. And we'll see why later on in this chapter. I can calculate the mean, and I get 14.95. So that's different than the one I had on the board, because every time we run it, we're going to get a different approximation. And I can calculate my standard deviation or my standard error, and I get 1.468. And that is also different than what I had on the board, because every time we run this, we're going to get a slightly different approximation. All right, let's do one more like this. I'm going to zip back to the board and then back to R. So once the light adjusts, it's getting pretty good. I want you to pause, copy it down, and then press play. All right. So it's very bright. So in this example, I'm going to look at the uniform distribution from 0 to 1. And if you recall from 313, the mean of that distribution is 1/2. And the variance is the b minus a quantity squared over 12, which in our case would give us 1/12. Okay. So how I'm going to do this is I'm going to sample 12 values from that distribution. And my test statistic is going to be the maximum of those 12 values. Not the mean, not the median, not a trim mean, just the maximum of those 12 values that I grabbed randomly from U01. I'm going to record that test statistic, and I'm going to repeat this process 10 to the 4th times. I'm going to have R do it, and I've got a couple of expected value of the test distribution, test statistic, and standard error approximation of the test statistic of these two values. And these will be different than what you see on the screen, because every time we run it, it's a different approximation. Okay. All right. So let's see how R can do this for us. All right, so this is example 4.3, starting on line 43. So first off, in line 45, 10 to the 4th is 10,000. So I'm going to make a vector with 10,000 spots in it to record my test statistic. And then lines 47 through 51 give me the loop running 10,000 times. And if you note, I'm going to name Y the random selection in the uniform distribution of 12 values. So that's R uniform parenthesis 12. If you just say unif, it assumes you mean the standard one from 0 to 1 unless you tell it otherwise. I want the standard one from 0 to 1, so we just need the unif again. So random from the uniform distribution, grab 12 members, and then I want my test statistic to be recorded. That's the max of Y. I'm going to put it in the vector in the ith spot. Okay, so I'm going to report 10,000 of these max values. All right, so let's run that loop. Doesn't take long. Now I can histogram it up. And there we go. And you see it's sort of definitely left skewed. It has a big tail on the left, and it's bulked up towards 1, which makes sense because we're grabbing the maximum value, these 12 randomly sampled between 0 and 1. So it makes sense that the maximum would be somewhere like 0.8, 0.9 in that area. Okay. I can calculate the mean of my 10,000 values of the test statistic, and I get 0.9236. Pretty close to what I had on the board. And the standard deviation, which is the standard error, I get 0.0705. That's also pretty close to what I have on the board. Okay. All right. So that concludes this video. All right. So that's the end of section 4.1.